Thank you, Sepideh. Thank you all for being here. I'm very happy to join this research group. So I share my screen. I have some slides, just few informations. So, okay, is it okay? Can you see it? So I'm going to make today a very general introduction to probability and decision theory. What I'm going to stress is this relation between probability theory and decision theory within this framework of game theory. So framework of strategic interaction. And at the end, I will comment on Ray Kurzweil's theory of technological singularity to see that it is actually inscribed in this decision theory and also in this game theoretic framework of strategic interaction. So, I mean, I will try to show the connection between this theory of technological singularity and the imperative of contemporary market. So, okay. Yeah, the problem is a problem of uncertainty, I think. I will try to explain why are we experiencing an increasing uncertainty today, even though we have the most developed technologies for predictions. So for me, this is a kind of paradox, this idea that we have the most sophisticated predictive technologies and still we are in a sort of increasing uncertainty. So I will try to explain in some way why this is the case. And also this idea is, the idea is to challenge the perspective according to which there is a connection between uncertainty, freedom, and creativity. And I will try to show that it's not really the case. But before commenting and draw the conclusions, I'm going to start really from this relation between probability and induction, so inductive reasoning. So basically, probability theory existed since a long time ago. I mean, the Greek knew probability theory, but they didn't need it. So the first treatise on probability was made by Girolamo Cardano in the Middle Age, and it was about games of chance. So it was a book on gambling strategies. So basically, probability theory was connected with gambling. So the first treatise on probability were treatises for games, for gambling, for betting strategies. So probabilities was just a tool for this kind of game, and they still are. They didn't lose this connection with gambling, bets, and game. So what I'm going to show is that there is a connection between the reformulation of the theory of induction and the attitude of a gambler, where the attitude of a gambler is to calculate the probability of future outcomes in order to make the best possible decision. So the idea is to maximize the expected utility by making the best decision with respect to the probability of realization of future outcomes. So that's also the reason why probability theory is really connected with economics. Okay, so the old problem of induction, so David Hume's problem of induction was about making generalizations from the particular to the general. Of course, there was no possible certainty, meaning that we can produce expectations about the future, but basically there is no reason why we can believe or we can trust our predictions. Even though we suppose that there are regularities in nature, we cannot demonstrate the necessity of these regularities. So we are going to see that the problem of induction has been reformulated thanks to probability theory, because probability theory is an important mathematical tool which allows to measure uncertainty. So to really measure what we don't know, to measure our ignorance in some way of the future. So I'm going to start with the basic probability theory, which is probability, which is called objective, which is based on frequencies. So this entails a little reformulation of a problem of induction. So it has been, probability has been introduced in science in order to account for stochastic processes. In particular, they have been introduced for statistical physics, when it's not possible to determine exactly the states of a system which is composed by a large number of particles. So the idea is to calculate the probability of different states of a system. So the idea is that there are stochastic variables in nature, like dices or roulettes. So the goal is to try to understand what the variable is by observing the results. It's like we observe, you see the image here, we have the some numbers, 1, 2, 3, 4, 5, 6. And the idea is I have these results, in a random order, like stochastic order. And I have to make my hypothesis about the variable. So this is a regular dice. So I have to observe the results of the throws of the dice, and I have to make an hypothesis about the variable. So is it a dice? Is it a roulette? How many possible outcomes? And is there an order? So can I predict the next one, or is a random process, so I cannot predict the next one? So of course, in order to make a correct prediction, we would need an infinite series of trials, which is impossible. So von Mises introduced this idea that we can do this with partial observations. These partial observations are series of outcomes that he called collectives. So collective is a series of results like this. If we don't find any rule to make predictions, we can consider that the results are stochastic, so that there is a stochastic variable. And of course, we have a limited number of possible outcomes, so it makes the universe or the domain. So the idea is that we, in order to calculate the probability, of course, we need to be sure that the series is a random one, because if it's not random, there is a law. If we can predict it, there is a law. Here, the idea is that it is really like with dices or with coins. When one flip a coin, the fact that we have tails 5 times does not imply that we can predict the next one. So we have 50% probability of any result at each row. So we cannot use the previous results in order to make an accurate prediction of the next one. What we know is the probability to have some of the possible outcomes or results at any throw. So in the case of a dice, we have 1 on 6 at any throw for 6 possible results. So the definition that Richard von Mises provided is that a collective is this kind of random series, and that it is such that no possible system for play is possible. So no martingale, so it's not possible to create a system in order to be sure, to make sure to win. So it's really connected with gambling and betting. I don't have here the quotation, but really von Mises made these examples with the casino and betting strategies, and it tries to show that a collective is this kind of series that we cannot predict. So we cannot be sure, make sure to have a strategy to win. We can only calculate the probability of the results of the next throw. So the probability is always the same. So we have equal probability for any of the possible outcomes. So in the case of a dice, we have 1 on 6 for each number at any throw, which is really easy and basic. But we have some problems with this. I'm going really fast because I'm just make a sort of introduction. Then if you have questions or you want to go deeper in some of the topics, we can do this later. So there are problems, of course, in this interpretation. So in order to use it as an inductive theory, first is that in order to calculate exactly, to verify if the series is really stochastic or really random, we would need an infinite series of trials that we will never have. Another problem, which is more serious, is that we can calculate the probability of events for which we have frequencies, so events that happened many times in the past. So we can evaluate the different value of the realization of these events. So we have frequencies, but we cannot use it in order to predict rare events. So we cannot use it to predict events for which there are no past frequencies. And the most important events are actually the events for which we don't have frequencies, like crises, catastrophes, and rare events, which are much more risky and dangerous, but we cannot calculate their probability with frequencies because there are no frequencies. So these events that if they happen just once, history is over. We cannot use this approach. Moreover, we just have a probability distribution. So we know the probability, the respective probability of different outcomes in an infinite time. So for a dice, for example, I can say, okay, number 5 will appear, but I cannot say when. I just say, okay, in an infinite number of trials, it will appear for sure, but I cannot say what will happen tomorrow or at the next row. So we have just a probability distribution, but we cannot predict a specific event, the probability of a specific event at a specific moment. Then Jean Ville, who was a French mathematician and also a gambler, demonstrated that actually with Moises' definition of a collective, it was possible to produce a gambling winning strategy, so a martingale. So the axioms are not strong enough to avoid any system. So he decided he tried to help this idea and say, okay, we can say that a random series or a random variable has to be we can prove that it's a random series by trying to make a martingale or try to make a game system. The problem is that this is an a posteriori system, not a priori. And of course we cannot define what a stochastic series is. This is the basic idea, because a stochastic series is a series for which there is no rule. If we find a rule to define a stochastic series, is no more a stochastic series. So this is a kind of problem with this approach. So we will never know if the dice is a regular one or, like this, is a not regular one. So we have another approach which is meant to correct these difficulties in the frequentist approach, which is the logic interpretation of probability. I'm introducing Carnap's theory, but it's older than Carnap. So for example, John Maynard Keynes was one of the first to introduce this idea of logic probability in his dissertation in Cambridge. So his dissertation was a treatise on probabilities, and he basically introduced the idea that probability is a measure of the implication between sentences. So the sentence is about the evidences, and the sentence which is the prediction. So probability is a measure of the degree of implication between two propositions. So of course we have analytic propositions, So they are certain, no problem, but we can have different degrees of implication. So probability is a measure of this degree of implication between the proposition describing the evidences that we have and the proposition expressing a prediction. And of course, Keynes' economic theory then is based upon his logical vision on probabilities, because of course, there are probabilities that we can measure, a probability that we cannot measure. And this idea that probability is a measure of a degree of implication means that we have some certainty about a prediction when it can be analytically deduced from the premises. And we have, on the other hand, some kind of predictions which are not supported by the evidences. For example, the probability of a war in 10 years. We can have a lot of evidences, a lot of informations, but there is no logical implication between any information whatsoever and the prediction that there will be a war. So according to Keynes, we can make economic plans based on logically entailed predictions, but not on predictions which are not supported by evidences, so which are not implied by the available evidences or informations. And we will see later that Bayesian probability theory, which is basically the ground for the model of rational agents in Friedman economics, will overcome this problem that we have in Keynes by allowing market speculation without any limit. But let's go back to Carnap. So Carnap wrote this big book, Logical Foundations of Probability. It's a sort of re-elaboration of Keynes and other mathematicians' probability theory, logical probability theory, logical interpretation of probabilities. So for Carnap, the basic idea is the same. So the probability is a measure of a degree of implication between propositions. So a proposition concerning the available evidences and the proposition which is the hypothesis of the prediction. So the idea is to find the degree of confirmation of theories. Of course, it's a way of collecting information or evidences that confirm the hypothesis. The important thing in Carnap is that introduce two terms for probability, so probability 2 and probability 1, and this is a really important distinction. So probability 2 is the frequency. Probability 2 is for example, the hypothesis that if I throw a dice, I will have 1 on 6 probability of observing any outcome. Probability 1 is the probability of the hypothesis, of a probabilistic hypothesis. If we go back to the example of a regular and irregular dice, this will make sense, meaning that given the frequencies, it's really difficult to be sure that we are really playing with a regular dice, so that the series is really stochastic, because we will need an infinite series of trials. So for Carnap, the idea is to evaluate the respective probability, so probability 1 of the two hypotheses. Is the hypothesis that the dice is regular more probable than the hypothesis that the dice is not regular? So probability 1 is a measure of a probability of a probabilistic hypothesis. So a probabilistic hypothesis is a probabilistic forecast. So there is probability 50% that will be rain tomorrow. Probability 1 is the probability of this forecast. So for example, you know that you have different weather forecasts. If you look at different weather forecasts, you have different probabilities for the rain tomorrow, for example. So the idea is to evaluate the probability or the degree of confirmation of the two different probabilistic hypotheses. So for Carnap, the idea is to evaluate the probability of the two forecasts, the respective probability of the two forecasts. To do this relies on this theory of confirmation. So the idea is to measure the degree of implication between evidences and hypotheses. So the idea is to evaluate the two different forecasts or more forecasts, to evaluate them with respect to the implication between the collected evidences, so the information on which the forecast is based, and the prediction. And according to Carnap, it's possible to show that there are hypotheses or predictions which are logically better logically supported, given the propositions concerning the evidence. So the ground is the body of knowledge. So we have in science some theories which are more fundamental than others. So it provides a system, a logical system, an axiomatic with definitions of basic terms, which are observational terms, and sort of hierarchy. So a new hypothesis or a new prediction should be entailed by the more fundamental definition, so entailed by the axioms and by the definition of basic terms. So it's possible, according to Carnap system, to evaluate the different degrees of confirmation of different probabilistic theories. So the idea is that while a prediction based on frequencies is an empirical one, so it's just an inductive theory, so there is no certainty which is attached to it, so it's just an inductive theory. We can ground it on logic, so we can accept or reject theory a priori because of logical implication. So we can have a certain a certain degree of certainty which is not based on experience, but which is based on logic. So it says this for a statement of this kind, so a statement of probability 1, so the logical probability of a prediction, statement of this kind is to be established by logical analysis alone. So it is trying to correct this problem of uncertainty, which is connected with induction. And it is, of course, independent of the contingency of facts, because it does not say anything about facts, but is just expressing a logical implication between propositions. Okay, so this is an important attempt. What for me it's important to remember is this difference between a probabilistic forecast, which is based on frequency and expected frequency, so expected regularity. So we expect in the future the same frequencies that we experienced in the past. And so this kind of probability and the probability of the probabilistic forecast. So is the hypothesis that we are playing with a fair dice logically confirmed or not? So the idea is anytime to evaluate if we are really believing that we are playing with a fair dice or with a stochastic variable or not. So the probability one is measuring the degree of belief or the confidence that a certain variable is really a stochastic variable or not. Then, of course, there are problems with Carnap's theory, in particular with grounding on logic. So if we recall Quine's critique, we know that, of course, first analysis that there are really that there are very analytic proposition is something which is dubious. Then we have a problem of a language for the evaluation of scientific theories. And a problem concerning the evidences. So basically, for Carnap, there is a strong relation between evidences and predictions, and we can measure the real implication between collected empirical evidences and predictions. But this is really difficult to prove. So, for example, there was this Hempel paradox. For Hempel says, okay, that all the ravens are black can be both demonstrated by the fact that I see all black ravens. For any new black raven will confirm the hypothesis that all the ravens are black, but also any other kind of observation is confirming this idea. So, for example, a red chair is confirming the idea that all the ravens are black because it's not a black raven. So anything can be a proof of an hypothesis. And more importantly, the problem is that we can use this kind of probability theory only to evaluate scientific hypotheses. So hypotheses for which we have a sort of some kind of logical relation or implication between propositions, but we cannot use this way of evaluating the probability of theory for other kinds of predictions. For example, I want to make a prediction about the result of the presidential elections. I cannot use logical probability theory because there is no evidence which implies strongly the result. And I cannot use it to bet on horses, for example, because I really don't know what is the information that supports the belief that one horse will win. And there is no possibility of establishing logically or rationally what is the information to take into account in order to make this kind of prediction. But in any case, this kind of prediction is really useful, and we do that all the time. So Bayesian probability theory is made for this, because Bayesian probability theory, as we are going to say, is a theory of rational decision making, even in cases like betting on horses, guessing the result of the presidential elections. So it's a way of making rational decisions for all the events in everyday life, even when we don't have any logical relation between the evidences of informations that we have and the prediction or what we expect. So the subjective interpretation of probability so Bayesian interpretation of probabilities is a subjective interpretation of probability. So one of the first was, of course, Bess in the 18th century. We introduced this way of interpreting probabilities. Laplace was Bayesian also, but then he died because it was too difficult to make the calculation at that time. So this subjective approach was rediscovered in some way by two mathematicians at the same time. So Frank Ramsay and Bruno de Finetti. We are in the 1920s and before the 30 in any case. So Ramsay didn't use Bess theorem, but he was on this subjective interpretation of probabilities, and he really makes this connection with probability and decision theory. So Ramsay was he died very young. He was 26 when he died. So truth and probability was his PhD dissertation, and his supervisor was John Maynard Keynes in Cambridge. So Ramsay probability theory is a kind of answer to Keynes' logic interpretation of probabilities. And of course, Ramsay says that the limit of Keynes' logical approach, which is really similar to Carnap's approach, is that this can be used only for predicting events for which we have some sort of logical implication between premises and consequences, so between evidences and hypotheses, but it cannot be used in all the other situations. When inductive method is way of reasoning, our method for reasoning in any situation in ordinary life. So induction is important because it allows to make a good decision in everyday life or any aspect of our life. So according to Ramsay, the probability of an hypothesis, so we are still in this idea that we are not just measuring the probability of an event, but we are measuring the probability of a probabilistic forecast. So probability is a measure of a probabilistic forecast, where given the available information, there are always more than one hypothesis which are available. So provided some information, we can say, okay, I expect this, but I can also expect this other event to happen. Both are supported by the available information that we have. So for example, I look at the sky and I have to say, okay, maybe it's going to rain or maybe it's not. So I have two hypotheses. I have to evaluate the respective probability of the two hypotheses by collecting more information or by evaluating the information that I have. So for example, I can consult the barometer in order to decide that the probability that it is going to rain is higher than the probability that is is not. So according to Ramsay, the probability of an hypothesis can be measured independently on the logical implication, and the way of measuring it is to observe decisions. So for example, I don't know exactly if it's going to rain or not tomorrow. So I am evaluating this hypothesis. But then at a certain point, I have to take my decision. So I decide to go out with my umbrella. So this revealed that I believe that it's more probable that it's going to rain than the contrary. So the decision is a way of measuring, the decision which is made by an agent is a way of measuring the degree of belief in a probabilistic hypothesis. And these kind of decisions are based on personal opinions and personal beliefs. And there is no necessity, so nobody can force somebody else to believe something, because basically there is no necessity or no logical implication between the evidences and the predictive hypothesis. So there's no way to prove in an absolute way. So all they are all beliefs. Of course, there are better beliefs and worse beliefs. And experience is a way of selecting more efficient beliefs. But the idea is that the framework is a pragmatic one. The framework is a pragmatic one because the selection of the best hypothesis is made because they are more useful than others. So for example, if I see that by consulting the barometer, my prediction about the weather are better than if I look at the birds flying, it's a way of selecting a better evidence or a better information, but because it's more efficient, not because it's necessary, not because there is a necessary implication between one of or the other. So the idea is to select the predictive hypothesis, which provides more chances of maximizing utility, so to make efficient decisions. So for example, in the case of the rain, my efficient decision is to go out with an umbrella if it's rain and without an umbrella if it's sunny. No, but it's the proof is the efficiency of the decision. And the other thing is that information is always partial, according to Ramsay. We will never have complete information, so we are always in a state of uncertainty because we don't have all the information which is needed in order to make a necessary probabilistic forecast. So we will never know if a certain variable is really stochastic or not. We can believe that it's stochastic and to a certain degree, and to have reasons to believe that there is a stochastic variable, like for example that the dice we are playing with is a regular one. But we will never get the complete certitude about this. So the degree of belief depends on the available information, and available information is always partial. But of course, we can select better hypotheses or more efficient predictions. So Ramsay proposed to measure the subjective degree of belief with respect to the decision that an individual is willing to take in order to get a preferred good. So there are two conditions, of course, to make a rational decision. The first is the order of the preferences. So an agent is making a decision in order to get the preferred option among the variables. And then he has to be coherent. So to explain this idea of the order of the preferences, we can make an example of, I mean, I am in a village because I have to meet a friend or to go to a friend's house. I went in that place just once, so I don't remember very well. I don't recall if I have to turn left or right at a certain crossroad. So I have two hypotheses: turn left or turn right at the crossroad. I have some information or some reasons to believe in one hypothesis or the other. There is no, of course, logical implication between what I know and the direction that I have to take. My preferred situation is to go straight to my friend's house, so to take a shorter time and go there directly without lose myself in the field. So the best scenario is to go straight to my friend. The worst scenario is to get lost. So I don't want to get lost. To get lost is what I have to avoid. In between, there is another option, which is I make a little detour to ask for information. So I see a person in the field, I have to walk a little bit, so I make a sort of deviation. So I waste some time, but I get the information which allows me to find the right path. So depending on the strength or on my belief, I will make different decisions. So for example, if I'm really convinced that the right way is to turn right, I don't make this deviation. So the fact that I go straight on the right means that I really believe that this is the right option. So my decision is rational because I strongly believe that this decision will allow me to get the preferred situation, so to avoid getting lost. And this means that I think that the more probable hypothesis is that the house of my friend is on the right. If I make a detour to ask for information, that means that my belief is not strong enough. So that is not the probability that I attribute to the hypothesis is too low to support a decision. So my decision is to get more information in order to obtain the degree of belief which is necessary to support action, so to support my decision. And this is a rational decision making because, of course, I want to maximize my utility, so to be in the best possible scenario and avoiding the worst. So if I judge that I have enough information, it is rational to follow my belief, my opinion. If I don't feel that I have enough information, it is rational to try to collect more information before deciding. So probability is this subjective way of evaluating the weight of the information that we have with respect to the viable predictive hypothesis, so the possible predictive hypothesis, considering that there is not just one predictive hypothesis given the information that we have, but we are always evaluating and comparing a plurality of predictive hypotheses, which are all supported by the information that we have. So it's subjective because there is no reason, absolute reason to believe in one option rather than another one, but it's a theory of rational decision making because there is this method of evaluating the chances and the decisions, which is the rational way of doing this. Okay, so I told that there are two conditions. So the first condition was the order of the preferences. So our preference must be ordered. The second condition is the condition of coherence. Condition of coherence is really difficult to be defined. The idea is that all the beliefs of a person must form a coherent set. So, for example, I cannot make decision following the hypothesis that the Earth is flat, and then make another decision which are contradicting my vision that the planet is flat. So all my beliefs must be coherent. So there shouldn't be contradictions in the belief of an agent. Of course, it's really difficult to prove a coherence, but this is a requirement for Ramsay. Okay, so for Ramsay, this way of evaluating the probability is the real method of induction. What is important is that the idea of the method of induction is changing a lot here, because we are not concerned with the reasons why we have regular expectations. So we expect that there are regularities in nature. So we know that for Hume it was impossible to demonstrate why there are these regularities in nature. So we do expect regularities, but we don't know if we don't know why we have to believe in regularities. Rather, for Ramsay, the problem of induction is, why do we have regularities of action? So why do we select regular strategies, or why we do regularly use the same kind of strategies or the same kind of predictions? So how do we collectively select a body of beliefs and hypotheses? So the idea is the problem of induction is rationally selecting strategies or selecting hypotheses to be used regularly by anybody. So this body of this set of beliefs is shared by humanity, and usually among the information that we have and that we consider before making decisions, there is also this set of beliefs which is part of common knowledge of humanity. So we are always creating our beliefs and our opinions about the future based on the set of shared beliefs in a community, considering that this kind of beliefs has been selected because they are efficient, so because they lead to efficient decisions. So what is important here is that the problem of induction is a problem of regularity in beliefs, rather than how do we obtain regularity in beliefs, rather than why there are regularities in nature, which is really important. Bruno de Finetti is another mathematician who talked about probability, subjective probability, and he introduced Bayes' theorem again, so the possibility of updating the beliefs. So for Ramsay, there was this update because, as we said, if the beliefs in an hypothesis is not strong enough, we have to collect more information in order to reach the degree of belief which is necessary to support a decision. Bruno de Finetti introduced Bayes' theorem to calculate exactly the way in which new information condition the degree of belief in an hypothesis. The ground is kind of the same, so there is no logical implication between evidences and hypotheses, because our evidences are always insufficient, always partial, and because basically the idea is to make a theory of probability for everyday life, for any kind of decision, not only for decision that we have a scientific ground to calculate the confirmation. So the idea is again that if we have some decision or some hypothesis which worked in the past, so that oriented successfully our decisions, we have to keep it. And yes, of course, this is important. Bruno de Finetti introduced this idea of this method, which is called method of the bets, in order to evaluate the probability as degree of belief. So for de Finetti, the probability is the degree of belief in an hypothesis. So the method of the bets allows to calculate the probability as degree of belief of an agent in an hypothesis. So it's really like the Ramsay method, but it's more mathematical, meaning that we can deduce the probability that an agent is attributing to an hypothesis by asking him how much money is available to put. So for example, if I ask somebody how much money will you put on the winner of the next World Cup in football, for example, the amount of money that you decide to put reveal how much you trust your hypothesis. So if you are pretty sure that your team will win, you will put a lot of money. If you are not too sure, so if you do not believe in your hypothesis, if this hypothesis for you is not really probable, you will put a little amount of money. So this is a method for measuring the probability that an agent is attributing to a probabilistic forecast. And of course, it depends on the subjective estimation of the quantity of information, of the available information. So if the agent thinks that he has enough information to trust his hypothesis, or if he feels that the information that he has is not enough. So for example, we can propose two bets. We can propose an agent to choose if he wants to bet on the winner of the next World Cup in football, or if he prefers to bet on the price of a stock in 6 months. The bet that he chooses reveal the field in which it feels to have more information. So if I'm an expert in finance, I will accept the second bet, the second challenge rather than the first one, and I will accept to bet on football if I think that I am an expert in football and I don't know anything in finance. Again, we have this criteria for of coherence, and De Finetti has also a way of defining coherence. So he says, if the beliefs of an agent are coherent, so if there are no contradictions in the set of all the beliefs of an agent, then no bookmaker will be able to propose any bet and be sure of winning. Otherwise, if an agent is not coherent, a bookmaker can take advantage, so can propose bets and be sure of winning. But of course, it's a way of measuring coherence, but a posteriori and not a priori. And to measure coherence a priori is really, really difficult. So the best theorem is this one that you see. It's a way of calculating how the new information influence the probability that an agent attach to different hypotheses. So to go back to our example of the weather, I have these two hypotheses, sunny or rainy. I can look at the sky many times, and anytime I look at the sky, the new information that I get make one of the two hypotheses more probable than the other. So if I see some dark clouds arriving, my hypothesis that it will rain became more probable than that it will be sunny. But there is a way of calculating this, which is the best theorem. Another important thing in De Finetti is the theorem of convergence, which is a way of solving the problem of induction in some way. So this convergence theorem says that if there are two agents who have different beliefs, so for example, one is believing that it's going to rain and the other one is believing that it's going to be a sunny day. So we are starting with different forecasts, different beliefs, different opinions, which are supported by their own reasons. If these two agents share the information that they have, so why do they believe an hypothesis rather than the other? So if they share the information that they have, so the reason why they believe in an hypothesis more than in the other, and then they share all the following observations. So if they observe the sky together, they will converge on the same probability. So they will select the same hypothesis as the more probable. And this explains why we have common beliefs, or why we have common knowledge. And this kind of common knowledge, the fact that we select the same hypothesis, is an effect of this converging theorem. So the fact that Bayesian agents are really sharing the information and sharing following information. And this is really important for scientific method, because even though two scientists are starting with different predictions, different hypotheses, so anyone is believing in his own predictive hypothesis, but they compare the information that they have and they make the same following observation, they will select as more probable, not as certain, but as more probable, the same hypothesis. And this is a way of selecting the hypothesis that anybody should believe. So the more rational hypotheses, which are pragmatically efficient hypotheses. So hypotheses which allows to make good bets, good decisions. So this explain the mathematical way, mathematically, because it's a mathematical theorem. So it explain mathematically how do we agree on beliefs. So it explains objectivity, the objectivity of knowledge on the side of collective agreement. So this is the reason why I said this is a way of solving the problem of induction, because rather than asking why there are regularities in nature, we are asking why do we have regularities in beliefs, and this mathematical formula basically explains why we have regularities in beliefs, and it's a consequence of the application of this Bayesian method for updating beliefs and sharing information. So even though the theory is really subjective, so there is no constraint, no rules for selecting the information which is which has to support some hypothesis. There is no way of saying, okay, you must believe this, because anybody can believe whatever he wants. And of course, the idea is that anybody believes something because he has to make decisions. So there is a personal interest. So I believe something because it allows me to make decisions that maximize the utility. So that allows me to find myself in the best possible scenario. But there is an objectivity, even though there is this subjectivity at the beginning, there is an objectivity at the end. So basically, there is a way of selecting through this mathematical process. There is a way of selecting the more reliable hypothesis has to agree on them. And this is the basic for game theory, of course, because in game theory, you know that agents are all rational agents, like Bayesian decision makers. And the goal of game theory is to make the best decision with respect to the decision of all the others. So agents has to predict the decisions of the other agents and make the best decision with respect to this anticipation of other agents' decisions. So, for example, in the prisoner game, the two prisoners will win if they both avoid saying that they are guilty of the crime. But in order to make this decision, they have to predict that the other will make the same decision. So for what we said before, since there are beliefs that are shared, it's possible to predict. So rational agents can predict each other decisions and make the best decision with respect to the decision of the other, because they are basically sharing the same method. So game theory, so the notion of equilibrium in game theory is a consequence of this method for calculating the probability of hypotheses. But we will talk more about this later. So another important mathematician is Leonard Savage. He was also a Bayesian, and he wrote his book on statistics in 1954. He was an American, and he really used both Ramsay and de Finetti theory, and he systematized them in order to create the first model of a rational agent. And this model of a rational agent is based on the idea that we can predict the behavior of a decision of a rational agent by supposing that it will act in order to maximize the utility. So in order to make the decision that will allow him to get the preferred good. So as we said with Ramsay, we need an order of preferences. So the agent will make the decision that will allow him to be in the best possible scenario while avoiding the worst. So this is a matrix which is used also in game theory. So we have an agent, so it's half in French and half in English, sorry. An agent who has to make the decision of going out with an umbrella or not. And there are two hypotheses, it will rain or not. So as you see, if he has an umbrella and it rains, it will win, because it's okay to have an umbrella when it rains. So it maximizes the utility because it's avoiding the worst possible scenario, which is getting wet. So getting wet is the worst possible. It will win also if it's sunny and it doesn't have the umbrella, because it's the best possible scenario. So going out in the sun without the umbrella, even though it's better to go out in the sun with an umbrella than to get wet. So to get wet is the worst. Then we have, okay, I go out in the sun with an umbrella. It's a bit uncomfortable, but it's fine. The idea is to go out in the sun without an umbrella. So rain without umbrella is 0. Rain with the umbrella is okay. Sun without the umbrella is okay. And in the sun with the umbrella is in the middle. So this is the way in which a rational agent is calculating, is making the decision by calculating the probability of the future possible scenario. So if I'm pretty sure about the weather, I make the best decision. If I don't have enough information to make the best decision, I'm still trying to avoid the worst. So I have to make the decision which allows to be in the best possible scenario, or at least one of not the worst, to avoid the worst if it's not possible to be in the best. And in order to do this, I have to calculate the probability of future states of the world. So this way of calculating the preferred scenarios is called the utility function. So the utility function is the preference of an agent. So what an agent is trying to get. Of course, the obtention of this state depends on the decision that one is making, and the success of the decision depends on the scenario that will happen in the future. But the problem is that we don't know the future, so we have to exactly calculate the probability of a future state of a world in order to make the decision which match with this future state of the world. So the utility function of a person is a certain behaviorally defined expression of a value for him of experience to which it applies. The theory makes no attempt to brand some utility function as more appropriate than others, so anybody can have his own preferences. So the gustibus non disputandum est, which is, if you know, this is also the motto in neoliberal economic school. So, for example, Friedman is all about the gustibus non disputandum est. So an agent is rational, he can make whatever, he can make decision to get whatever he wants. There is no restriction about what one has to desire. But there is a sort of normative way of reasoning, which is this rational way of reasoning. And so utilities depends on the agent. And this also concern risk, for example. We can love risk or not. We can make very risky decisions because we love risk, so no problem. So a risky decision like financial speculation is not irrational at all. Is rational. Is just a way, it just a preference of the agent. Of course, he has to calculate the risk. He has to calculate the probability that his decision will succeed, which usually is a low probability of getting a lot of money. But this is not irrational, for example, according to Savage. It was irrational for Keynes, for example, because risky decisions are decisions which are not logically, so it's decisions which are supported by hypotheses which are not logically implied by the premises. Here, there is no problem because there is no these hypotheses are not based on logical implication. So utilities express values or tastes. So a person's system of personal probability expresses his opinion in an arithmetic way. Of course, the decision of an agent reveals the preferences. And this is really important. Anytime an agent make a decision, provided that we are in the same frame of shared information and observation, so we can really observe the decisions of the others, and the others can observe our own decisions. If there is this reciprocal observation, the decision of an agent basically reveals the preferences. And this is really important, for example, in the market, meaning that my economical decisions are revealing my tastes. So what is my utility? What is the good I'm trying to get, what I want to achieve? And this allows to make predictions about behaviors. Then okay, so the idea is that there is also the possibility of modifying the degrees of belief for Savage by applying Bayes' theorem. Again, two individuals concerned with the same problem but starting with different degrees of belief will converge toward the same opinion after having observed the same results. This allows scientists to converge on the same theories by observing the results of the same experiment in such a way to agree on what is reasonable to expect if a specific protocol is followed. So according to Savage, it's possible to achieve this agreement even though it is not a necessity. So for De Finetti, it wasn't necessary, this agreement. For Savage, no. For Savage, there is a condition for this agreement, and is that we can basically make good predictions and converge if we are in a limited frame. So if we have a limited number of options, otherwise we cannot calculate, because if the matrix is too big. So we had, for example, this matrix here, which is really simple and easy. Anybody can basically calculate what is the best decision with respect to the probability attached to the hypothesis, no problem. But if we have more options, it's of course not doable by our minds, at least. And so that's the reason why we need artificial intelligence and technological systems of prediction to be able to frame a large problem into a small matrix and to be able to calculate. So this model of irrational agent was introduced by Savage in the 50s. Was inspired by Ramsay, De Finetti, but also from von Neumann and Morgenstern game theory. So it's the agent who is basically able to make the best possible decision with respect to the available information. So the idea is that we don't have to make the right decision, but the best possible decision with respect to the information which is available, which means that if we get more information, we modify our decisions. And this is the way in which we make some progress. So by accumulating information, we can modify our plans, so our decisions for the future. So what is rational with respect to the information that we have. So it's not absolutely true, but it's the best we can do with respect to the available information. So the idea is that there is no true and false, but more efficient as less efficient. So the idea is to improve the chances, the probability of making good decisions, so maximizing the utility by collecting more information. Then Friedman, when he introduces theory of positive economics, which was based on the irrational agent. So he considered that any agent in the market is a Bayesian decision maker. This model for rational agent is inspired by Leonard Savage. In fact, they wrote 2 papers together. One of his papers is a paper that explains why we can predict the behavior of rational agents by assuming that they are acting in order to maximize utility. Okay, so now we have a different kind of theory I mean, it's connected, but this is the other side. It's the first predictive machine, which was produced by Ray Solomonoff. So I think that in order to understand the kind of rational agent that artificial intelligence is, we need to put together again theories of this theory of decision making based on probability, and this Solomonoff's theory of complete induction. So Ray Solomonoff was a student of Carnap in Chicago. So all these people were in Chicago, which is kind of explaining a lot. In Chicago in the 50s. So Solomonoff was a student of Carnap in Chicago. Again, he was against this logical interpretation of probabilities for all the reasons that we said before. And his idea was to create this machine to make inductive hypotheses automatically by relying on Bayesian inductive inference or statistics. So by automatizing this updating of the beliefs thanks to the information. So the idea is that a machine can produce a large number of hypotheses by exploring the data which are available. So a data set can support different probabilistic hypotheses. So the machine can collect more and more information in order to select among the possible hypotheses, the hypothesis which is more probable, which means also that it's possible to include new information. There is no decision making in Solomonoff, but it's kind of a consequence, because when we have the best predictive hypothesis, then we have the possibility of making also the best decision. What is important, so he used a Turing machine because it was the 50s, so it didn't have a lot of technology at the time, but the way of reasoning is still valid. I'm trying to go a little bit faster. What is interesting for me is this idea that is considering that any inductive theory is a theory about a series of outcome. So as we said before with the dice, what is important is the series of a possible outcome. So is considering any event as a series of outcomes, of possible outcomes that can be produced by an algorithm. So in the case of a random variable, so like a regular dice, there is no algorithm that can produce it. So it's random, but for most of the natural events, there are some kind of laws, so we can make predictions. That means that we have possible outcomes, and these outcomes can be produced by an algorithm. So a law of nature, according to Solomonoff, is an algorithm which is able to produce an ordered series of values. So for example, if we have to make a prediction of the viral contaminations, we usually have the plot of a curve. So an algorithm can produce this kind of series of values. In order to get this theory, so in order to get the hypothesis, and the hypothesis for Solomonoff is the algorithm which is able to produce this series of results. In order to get this hypothesis, the idea is to explore a data set to find regularities. So in any data set, there are a lot of different regularities. So for any data set, we can imagine different rules or different algorithms that order the series. And then the idea is to use best theorem in order to select the best one. So any phenomenon is identified with an information structure that can be generated by a recursive function or by an algorithm. And as we will see, this idea that anything is a pattern of information that can be produced by an algorithm, by a recursive function, is what is supporting, for example, Ray Kurzweil idea of technological singularity. So ontologically, everything is a pattern that can be produced by an algorithm. So everything is a matter of computation. Anything is basically information. So of course, when we have the algorithm of this recursive function that produce all the values of a series that represents an event, we are able to predict the unobserved values, so unobserved events. What is difficult then is to be able to select the best hypothesis for any kind of event. And according to Solomonoff, and I think that this is really important, there is no way of obtaining inductive certainty by this method, or at least by computation, and introduce this sort of incompletude theorem for computation. So we said that we need to explore a data set to find all the hypotheses that so all the hypotheses means all the algorithms that can produce the ordered series of the values, to find an order in the data set, to find the rule that produce all the data that we have. For any data set, we have different plurality of hypotheses or options, and we have to calculate the respective probability of different options by using Bayes' theorem. The problem is that we will never be sure that we will find all the predictive hypotheses which are supported by the data that we have in a data set. So when we are using just a limited number of hypotheses, our calculation is wrong. So there is some mistake. So, and we will never know if we get all the possible hypotheses. So we will never know if we are calculating or if we are taking into account all the possible hypotheses which are supported by the information in a data set. So there are mistakes if you're not taking into account all these hypotheses. But what is more dangerous is the fact that so what entails the impossibility of complete induction is the fact that we really don't know if the calculation will stop. And there is no way to know if the calculation will stop before running this. So according to Solomonoff, a system, a set of inductive hypotheses which is computable is incomplete, and a system which is complete is uncomputable. So this does not mean that we don't have to use inductive method. This only means that is useful, and that we have to take into account the possibility of mistakes and also the impossibility of obtaining inductive certainty. So we will be in a sort of, I'm not saying uncertitude, but it's not uncertain, almost. So we can at least calculate the degree of certitude of our theories. So the idea is that we will never get certainty. We can use this method for calculating probability to calculate the degree of certitude or uncertitude of the different theories. But there is no certainty that can be produced by inductive method, because it's an inductive method. So there is no basically solution to the problem of induction. So we can converge, we can agree, we can select hypotheses. This means that they are good enough to make decisions, so that the decisions that we make by following the hypotheses that we selected are good decisions. So they allow us to maximize utility, the expected utility. This does not mean that we are sure to win, but means that we can calculate the risk exactly. No, to make a good decision does not make a successful decision 100%. It means that I know that I have 60% probability of getting the result that I want. So I'm calculating the risk. This is the meaning of a rational decision in a situation of uncertainty. So also Bayesian agents in the market, they are not have the knowledge to always make the decision that allows to win, but they can assess the risk exactly. So they know exactly that they have, for example, 80% of probability of getting the result that they want. It's like with gambling, no? With gambling, we will never know that we will win for sure if it's a fair game, of course. But we can make rational decisions, so because we calculate the risk. So the idea here in Solomonoff is that, okay, a complete system is uncomputable, and a computable system is incomplete, so we will never get certainty. But we can take this into account in order to calculate the risk which is entailed by our decisions, in order to have insurances, for example, or to have protections against the risk. And that's why the model of a rational agent is the model of the agent in the market, because the idea is that the risk is calculated. So there is a difference between risk and uncertainty. Uncertainty is a situation where the risk cannot be calculated. So when we have an unpredictable random process, for example, there is no uncertainty. So a game of dice, it's not uncertain because we can calculate the risk exactly because we know the probability of the result of any throw, so we can calculate the risk. Uncertainty is when we cannot calculate the risk. For example, if we cannot decide if the dice is a fair one or not. When we cannot decide if it's probable enough that the dice is a regular one, we are in a situation of uncertainty because we cannot exactly calculate the risk. So we are in a situation where we cannot make a rational decision. So in that case, rather than making a decision, we have to wait until we collect all the information which is needed in order to decide which theory is more probable. So game theory, for game theory, what is important for me is the notion of equilibrium. The notion of equilibrium is a situation in which any agent makes the best possible decision with respect to the decision of all the others. In order to do that, any agent has to predict the decision of the others by supposing, by knowing the preferences of the others. So usually in a game, preferences are given. In a situation of equilibrium is interesting because since anybody is making the best decision with respect to the decision of all the others, anybody has the same chances of maximizing utility. Like if we are all playing with the same regular dice, we are not all winning, but we all have the same chances of winning. So a situation of equilibrium is a situation in which anybody can calculate the risk of his decisions when the success of a decision depends on the decisions of the other. So an economical decision, for example, will be successful if I can predict the consequences of the decisions of all the other agents. But by supposing that all the agents are rational decision makers, like Bayesian decision makers, it's possible, in theory at least, to predict the behavior so that anybody can make the best possible decision. So anybody has the same chances of maximizing the expected utility. So equilibrium is a kind of convention in David Lewis sense, meaning that a convention is grounded on the fact that agents behave in some way because they expect that everybody will behave in the same way. So for example, the fact of driving on the left or right side of the road is a convention. It's a decision, and anybody's making this decision because it's the best decision with respect to the expectation that the others will make the same decision. When we are in this situation, nobody has interest to deviate because deviation from a convention or from an equilibrium will entail losses for everybody. So the problem of this notion of equilibrium is that once we are at the equilibrium, we are stuck in some way. So there is no possible evolution. Because a situation of equilibrium is really predictable, basically. it's really predictable, even though anybody can believe whatever he wants. So, I mean, preferences are different for anybody, so anybody can decide to get any kind of goods, and there are no restrictions about the information to be taken into account. At the beginning, at least. Okay. So from the so game theory has this idea of convention. So agents just select the behavior which allows anybody to maximize the expected utility. So, for example, in the case of driving on one side of a road, is a way of avoiding accident for everybody. In the case of the market, is more complex. A situation of equilibrium in the market is a situation where agents can be modeled as they were making decisions in order to maximize the utility. And anybody knows that anybody knows that. So they can predict each other behavior. The information which is pertinent to make this decision is the observation of prices. So prices are supposed to convey all the information which is needed in order to predict the decisions of the others, because they reveal preferences. So, for example, if a price is going up, we can deduce that this good is preferred by a lot of agents, and we can predict that another good will be less preferred. So we can, by knowing preferences, we can also predict decisions. So in this situation of equilibrium, prices are providing all the information which is needed. So variation in prices allows to condition the probability of different hypotheses. So, for example, the hypothesis that hypothesis concerning the future can be taken by observing the variation of prices. That does not mean that one will guess the prices of the future, because they are random. But this means that anybody has the same chances of making a winning decision. So there are no privileges, and so anybody has the same chances of maximizing utility. So nobody has the interest to deviate from the equilibrium. So nobody has the interest to take into account other information. So they are all taking into account only the information which is provided by prices in order to make their decisions. So this is the convention. Of course, the problem is that once we are in this situation, the market is stuck. So there is no possible evolution of the market. The only way of making the unequilibrium evolving is that there are some exteriority, so perturbations of equilibrium, like external events. And this is the reason why we have evolutionary game theory. Evolutionary game theory is more recent, is a more recent theory of games, and it's based on the idea that there is an historicity of equilibrium. So there are changes in the situation, and the idea is that there is a competition in the market which is not a competition among Bayesian rational agents, but it's more about different strategies competing each other, and there is a sort of natural selection of the best strategies. So strategy which is not adapted disappear, and strategies which are more adapted replicate. So there are these sort of evolutionary equilibria. So these equilibria are never optimal. This means that they can continue to evolve, and they are unpredictable. So a classic equilibrium is predictable, meaning that agents realize this a specific game theoretic equilibrium because they are all predicting it. In this case, equilibrium is not predictable, so the evolution is not predictable at all. Can be simulated by genetic algorithms. So we make the simulation, we let the simulation running, and we see the unfolding, but it's not analytically, cannot be analytically deduced from the premises. In any case, what we get is that by running these kind of programs, we can observe that the same kind of classic equilibrium can emerge at certain points, and then they can also disappear. So there is a way of considering the evolution of a market like natural evolution. So we have different routines and different technology which are competing in the same way as different animal species are competing. And for animal species, for example, the species which is spreading, which is reproducing a lot, is kind of winning. And a species which is not reproducing and that disappears, not well adapted to the environment. In the case of the market, is the same. So we have technologies, routines, and ways of production. They are competing against each other, and there is a selection of the most reciprocally adapted strategies. Reciprocally adapted strategies create patterns of interaction which are more or less stable. Usually stable, but not definitely stable. I mean, they can change because they are not optimal. Usually they are just strong enough to survive for a while until new strategies are introduced, because always new strategies can be introduced. It has to be introduced. So the introduction of a new strategy is like the invention of a new technology. So the idea that, like in evolutionary system, we have a mutation, for example, so a new kind of behavior, a new kind of approach which enter a game. If this new strategy is more successful, it will cause the loss of other strategies, so the disparition of our other strategies, and a modification of the whole equilibrium. So in evolutionary theory, choice sets are not given, and in consequence of any choice are unknown. So there is a way of testing new strategies without knowing that the new strategies will be a winning one. So there is no choice which is clearly best ex ante. So there is no calculation to introduce the best strategy with respect to the strategies of all the others, because usually there is no this knowledge of of the strategies of all the others. And so one would expect to see a diversity of firm behavior in real situations, meaning that anybody's kind of following a strategies and trying to see if it works or not. And then there is this sort of natural selection of strategies. And different agents are characterized by specific routines or schemas of actions, which are compared to genetically determined behavior like different species in Darwinian evolution. And then this is evolutionary game theory. We can adapt this to the market. So there is also this evolutionary economics. In evolutionary economics, the market is really modeled like this sort of competition between agents with bounded rationality, meaning that they cannot basically anticipate or make correct prediction of the decisions of the others. So they can, when an equilibrium is obtained, because usually the idea is that it starts with a competition, then there is the selection of the reciprocally adapted strategies. When there is the selection, there is an equilibrium, so everything is predictable at that point. But what cannot be predicted is the emergence or mutation or the introduction of a new strategy, of a new technology, which basically force all the others to adapt again. So it pushes the system out of the equilibrium until it reaches another equilibrium. So it's predictable at some points because there are multiple equilibria, but it's not predictable in the long term, and cannot be analytically deduced from the premises. So it seems that it's really creative, and that we can expect anytime something new, new equilibria, new strategies, new trajectories for the system. And also explains this, what we see, so history of the social organizations, and also diversity of situations. The equilibrium can be more or less robust, so it depends on how long they last. So the word seen by evolutionary theory differs from an orthodox word, not only that things always are changes in way they could not have been fully predicted, and that adjustments always are having to be made to accommodate to or exploit those changes. It differs as well in that those adjustments and accommodations, whether private or public, in general do not lead to highly predictable outcomes. For better or for worse, economic life is an adventure. This is a quotation from Nelson and Winter, who are the pioneer of evolutionary economics theory. So with respect to this, I think it's important to consider another theory, which is the theory of economy of information, which was introduced by Grossman and Stiglitz in the 80s. So in the 80s, it was clear that classic equilibrium was not working at all. So the idea that all the agents make the best decisions with respect to the decisions of all the others, that the prices transmit all the useful information and anybody can just act rationally and maximize the utility was something that, okay, was not working. It was not true. It was a kind of jungle already. Meaning that this does not mean that the market is stochastic. It means that it's not stochastic. So in the theory of equilibrium, prices are moving according to a stochastic yes, it's called a random walk of prices, so they are unpredictable, like a dice, like a fair dice. So a market at equilibrium is called a fair game because it's like a game of dice. It's unpredictable, it's random, like the outcomes of a dice. This means that anybody can calculate the risk exactly, and that anybody has the same chances of winning. When we are in a situation of excess of volatility, for example, the prices are going out of a prediction. So it's like, for example, I have a dice, I expect values between 1 and 6, and suddenly I have an 8 which appears. I say, why 8? I was supposed to play with a dice with 6 faces, and now there is an 8. So excess of volatility is like an 8 appearing on a dice which was supposed to have 6 faces. This entails that the risk that was calculated is no more effective. So I made my bet with respect to the expectation of 1 on 6 probability. So I make my bet by taking into account a certain risk, and then the risk is different from my prediction. So there is a situation of uncertainty and no more risk because it's not possible to calculate it. So it's because of this situation of excess of volatility that the theory of evolutionary economics was introduced to say that, okay, maybe there is an equilibrium and sometimes it works, but there are no reason to believe that the equilibrium will last forever, because there are endogenous rather than exogenous causes of change. And these endogenous causes of change are just the introduction of new strategies, of new routines, of new technologies. And these new technologies which are introduced cannot be predicted by the agents, but they have effects, unpredictable effects. So once a new strategy is introduced, there are unexpected effects on the market, and the idea is that it's necessary to adapt to this change. Some technology will disappear, some other will appear, and the overall organization is going to change. This idea of economy of information is really interesting because it takes the same situation from another standpoint, meaning that okay, it's explaining that basically in a situation of perfect equilibrium, there is no economic growth. So in a situation of equilibrium, it's just stuck. So the game is going to repeat itself, but there is no economic growth. Moreover, it's not possible to develop a financial market, because for a financial market, what is important is that beliefs are not homogeneous. So expectation should be different. So beliefs and expectation must differ. And the idea for Grossman and Stiglitz is that what is the real reason for this uncertainty in the market is not just that agents are kind of rationally bounded, so they cannot calculate. They were like just stupid animals. We are just competing like algorithms, and then a solution will appear magically and suddenly without them to be able to make any rational decision, like in the evolutionary system. The equilibriums just appear. Selection is just a mechanism which goes, and agents, we're just playing their strategies, but they're not reasoning at all. Grossman and Stiglitz, on the other hand, are explaining this situation from the standpoint of rational agents, who are just unable to make optimal decisions because of an asymmetry of information. Meaning that, so we said that in order to converge to the same beliefs, Bayesian agents needs to share the information. And for example, in the classic equilibrium, all the agents can rely on prices as the pertinent information, which allows to make efficient decisions. So it's not that they are more intelligent, it's just that they are converging towards the same beliefs because they are sharing the same kind of information, so they can predict each other behavior. But in a situation where information is not shared, and some agents have more information than others, it's clear that behaviors are reciprocally unpredictable. And in particular, this situation is obtained when information is costly. So information conveyed by prices was free, was public and free. But we know also that information which supports rational decisions, for example, in financial markets, is not free and it's not public. So Grossman and Stiglitz show that if there are agents which spend in order to acquire more information, which means that this acquisition of more information, so information which is not conveyed by prices, but some other kind of private information that can be, for example, forecast about people beliefs or preferences or whatever. If there are agents who can spend to get more information, and this information will allow them to make better decisions, this means that all the information which is needed is not public and free. But prices do not transmit all the information which is needed. And what is happening, they observe what is happening in the market is that there is this market of information. So there is a market of forecasts, not only forecasts in financial markets, but forecasts about everything. And this information is not free and public. So there is a way of extracting data, extracting information, and this information is costly because in order to extract this technology is needed. So it's an investment for the production of information. So in order to make it, to make a rent from this, one has to sell the information which is technologically produced. Then if I buy this kind of information, I need that this information is not sure, because if an information is known by everybody, it's kind of not information. But in order to be, to allows me to make better decisions than the decisions of all the others, it means that it must be used in a private way. So Grossman and Stiglitz are basically showing that this kind of innovation, technological innovation, which is kind of producing or causing, provoking the evolution of the market, is basically an investment for producing private information. And producing private information means also to produce new technologies. So introduce strategies, new strategies, which are not predicted by most of the agents of the market, which means that some agents are more chances of maximize utility than other agents who cannot afford to buy information, cannot afford to buy technology which is needed to get the information. And basically there is a market of information where information is not only produced for private use, but any money which is made by producing information is used in order to develop information technology and to introduce new way of extracting information and producing more efficient way of predicting the future states of the market. Because as we said before, the decisions which are made reveal preferences and reveal beliefs. So I cannot use, so I buy an information, a private information, for example, a forecast about belief of people, which is useful for me to make a good decision, because I can predict a situation that the others cannot, because they do not have the information. But once I use my information, so I make my decision, for example, I invest the $1 billion in some kind of action or fund or stock, the other will know what I believe. So I cannot do this twice. Okay, so when I cannot use private information without revealing it, so without making it public. This means that once I use it, I need to invest in new and more information, and also in new technologies to produce this kind of information, more sophisticated technologies to produce this information. So we have a situation where basically equilibrium is always changing, because new strategies are always introduced into the market, which makes the situation completely unpredictable. So not only unpredictable, but uncertain. But it's more uncertain for some agents than for others. So we have kind of bounded agents who are not able to make rational decisions, because they are in a situation of ignorance, because they cannot predict the decisions of the agents who are paying or are buying information that they cannot afford. So it's not that they are stupid, it's just that the new strategies of other agents cannot be correctly anticipated. And we have other agents who are basically investing to produce more efficient predictions and forecasts. And of course, it is efficient because they have more chances of, or at least they can maximize their utility, the expected utility. So they actually can make good decisions. They cannot win for sure, but at least they can make rational decisions. So we have some agents who are manipulated in some way, and others who have more information and more technologies who can make rational decisions. So the chances are not the same. And this also produces a sort of acceleration of the development of information technologies, because of course I need to invest in the innovation of the strategies to make them effective. So there is a sort of market of information, which is where information is a good. Is the good that anybody has to consume, because without consuming information, there is no possibility of making good decisions. In fact, we cannot make any good decision without the support of information technology to different degrees. And it also entails that we are forced to consume this, but while consuming this information, we are just producing new information. So by consuming information, we are in a gratuitous way most of the time producing information which is treated, bought, and used to introduce new strategies which create the need for more information. So I need to, for example, stay all the time on apps and the internet and whatever, because the information that I have is not enough. So there is a need for updating all the time the beliefs, all the time the information, all the time the knowledge. But by using these systems for getting information, I am producing in some way the information which is used in a private way by the people who can afford it, or can invest in it in order to make decisions that take advantage of the knowledge about my decisions, which is produced by my activity of consuming information. So it's a bit late, maybe. So I'm not unfolding too much of my conclusions, but my problem is that this theory of singularity, technological singularity by Ray Kurzweil, and this idea of this unpredictability and creativity of the evolutionary process is really a way of considering this kind of self-feeding system of information production and consumption rather than knowledge production. And okay, I selected some quotes from Ray Kurzweil, who is basically considering evolution in the same way as the evolutionary paradigm in game theory and evolutionary economics. So considering this competition like a competition between patterns or behaviors or technology which are competing, and there is a selection of them more reciprocally adapted with the possibility of introducing always new strategies. And there is this growth, which is the production of more ordered patterns, and more ordered patterns are patterns which are basically more efficient to for a purpose. So it says information is a sequence of data that is meaningful in a process. So the way of, okay, order as information that fit a purpose. So this increasing order is a way of introducing strategies or technologies which are more effective in providing growth. So growth means like the reproduction of a species, but as it says, okay, this is relative to a utility function. So the purpose is related to the utility function, so the preferred good. So it has this way in which we have an evolution in technological process, an evolutionary process of technology development. We could assign a measure of economic success. So this way of fitting a purpose, which is a purpose of developing technology itself to get further order, so to introduce more efficient, economically efficient strategies. So what is evolving basically is the capacity of introducing new economic strategies, basically in information economy. So information technologies encompassing an increasingly broad class of phenomena and will ultimately include a full range of economic activity and cultural endeavor. And well, I cannot go through everything, but what is interesting for me is that this law of accelerating returns, so it's translating the Moore law, which is this law of the acceleration of the development of technology, is calling this law of accelerating returns. And he says it's fundamentally an economic theory. Contemporary economic theory and policy are based on outdated models, okay? So it's the economic imperative of a competitive marketplace that is primary force driving technology forward and fueling law of accelerating returns. In turn, the law of accelerating return is transforming economic relationship. Economic imperative is the equivalent of survival in biological evolution. So we are moving toward more intelligent and smaller machines as the result of smaller advances, etc. Each with its own particular economic justification. So the idea is that, so there is this new knowledge-based economy. So for me, the problem is that, okay, there is an evolution, there is a continuous and accelerating change, but is this change really a way of evolving or producing something new, or is just this imperative of infinite economic growth, which is now supported by this economy of information, which of course allows for uncertainty, it's unpredictable, it's creative, new technology are always introduced, but the goal of this is not really to produce something else than a good, which is information. So the new information which is produced is like good for consuming. So it's a product, it's a commercial product. So that's for me is kind of the question, no? So I'm kind of questioning this idea of uncertainty, freedom, and creativity from this perspective of in the framework framework of information economy? Is it really technological improvement of knowledge and progress, or it's just that information is a new good, good for mass consumption, and what we need is to reproduce, not only to reproduce it, but to reproduce the need of consuming it, and the need of reproduce the consummation of information is uncertainty itself. So it's this asymmetry of information, this asymmetry of knowledge that stimulates the consumption of information, which is a good. So I don't know if it's really progress and freedom, or if it's just stimulating the consumption of a good and the reproduction of the same good without no knowledge value in some way. Okay, I stop here.
I guess I was asked to moderate. I just wanted to say thank you so much for this 2.5-hour primer.
Sorry, it was too long.
No, it was great. I just wasn't expected, but I didn't. For the sake of compression of time and your time and everyone's time, I did have some comments that I was like inscribing, and there were some people. I mean, David Roden and Martin had written their thanks for the talk, and that you've given them a lot